All right, we started talking about a couple days last Friday, circular motion, the idea of circular motion. Everything that we've talked up to now is the idea of a linear motion, or it can be reduced into a linear motion idea. Your trajectory motion, even though it's two-dimensional, we can reduce it down to a one-dimensional idea in regards to vertical or horizontal. When we go 3 dimensions, or when we go circular, we sort of move ourselves into a third dimension. And that third dimension is the dimension coming, excuse me, the dimension that's coming out at you. So you have an axis spinning that's coming out at you when we're rotating an object around a center point. That gives the third dimension, which is an axis coming out at you. So when we talk about circular motion, it sort of throws us into a third-dimensional idea. Just to review some of the ideas, circular motion, a motion that revolves about an axis. Once again, it takes us in the third dimension. Talked about an axis of rotation. That's the rotation coming out at you. Tangential speed is the circumference of the circle divided by the amount of time. We took distance divided by time. But we also talked about what we did in pre-calc, and we were in pre-calc, and the trig idea in pre-calc, we talked about angular velocity and angular speed. When you talk about angular speed, that is your rotations, revolutions per minute. That can, when we deal with our calculations, we have to change that into radians per minute. 1 revolution is equal to 2 radians, and we can do mathematical calculations in the idea of working through our velocities with our angular velocity in radians per minute. We also talked about a tangential velocity. Here is an average tangential velocity. It's how much distance we take for an amount of time. But we can also look at tangential velocity as the radius of your circular motion times your angular velocity omega. So these are all ideas that we talked about on Friday. The velocity of an object in the circular path is a vector drawn tangent to the circular path at any point. So we take a look at our velocities at any point. It is a tangential velocity. Once again, if I'm spinning this around and it hit a nice sharp blade where it cuts the string as it goes through, the object would continue to go in whatever direction tangentially it was at that specific point. Well, when we change our direction, it's continually changing direction, which means that tangential velocity is changing. So when you have a change in velocity, that means you have to have acceleration. Even though the average velocity still may be the same. The average tangential velocity may still be the same as it spins around. The instantaneous velocity is changing. Why? And that's because we have a change in direction. If we have a change in direction, we have a change in velocity. If we have a change in velocity, that means we have to have an acceleration at that point. Well, if we have an acceleration, when we take a look at the acceleration, if you have an acceleration, that means you have to have a force net. Okay, you have to have a net force. And if we look at the string here, the force that's being applied to this object is the string. The string is the thing that's keeping the object moving in a circular motion. Okay? So you have to have a force that's being applied here through the string to keep this going in a circular motion. Well, if you have a circular motion, or if you have an acceleration and you have a force, where's the force coming from? Well, it's coming from the string, so the force is being pointing in this direction and this way. Okay? So we have a force. If we have a force, we have to have an acceleration. Okay? So this acceleration is pointing towards the center of the circular path. So my acceleration is going into here, which means your force net is going to be going in that direction too. Okay, going back to Newton's first law. Sir Fig of Newton's first law deals with the idea of inertia. Inertia. An object will stay in the same state of rest or motion unless acted upon by an unbalanced force. Okay? Object will stay in the same state of motion or at rest in this linear path unless acted upon by an unbalanced force. That's inertia. Okay? If I didn't have an unbalanced force, this object would continue on a linear path. But it's not an unbalanced, we do have to have an unbalanced force to keep it going in a circular path. Okay, so we have this circular path here. We have to have unbalanced forces because inertia tells us this is going to go linear. So when we don't have inertia there, that means something has to be acting upon it to make it go in a non-linear force or direction. If velocity once again is changing, if velocity is changing, acceleration must occur. If velocity is changing, or if velocity is changing, acceleration must occur. Which leads us into the next idea of what is called a centripetal acceleration. A centripetal acceleration is acceleration occurring on an object in a circular path. It's acceleration occurring on an object in a circular path. This acceleration is changing the direction. It is changing the direction. When we have change in direction, we have a change in velocity. It is bashing and diminishing the idea of inertia. Because inertia tells us we're going to go in a linear force and linear direction. We are going circular here. It's not linear. So we have to be changing our velocity somehow. We have to have an acceleration change our velocity, and that acceleration is called centripetal acceleration. Now what you have maybe heard at some point and dealt with at some point is the idea of centrifugal. A centrifugal force, you might have heard of a centrifugal force before. This is not centrifugal, it's not an F in there, it's a centripetal. Okay, so there's a difference between centripetal and centrifugal. And to be quite honest, centrifugal is not really a force. But we'll talk about that here. When we talk about centripetal, it means center seeking. It's you're looking at and you're geared towards and you're aiming towards it's aiming towards the center of rotation or the axis of rotation. You're going towards and aiming towards that center of rotation or that axis of rotation that you're moving about. And how we can calculate the centripetal acceleration is your tangential velocity squared divided by the radius of the circular path. Your tangential velocity squared divided by the radius of the circular path. Which is Vt squared divided by r. Tangential acceleration occurs when the object changes velocity. So we can speed up and slow down as we go, and we get a pulse in there and it speeds up and slows down. Or gravity will eventually slow the object down. So when the object speeds up and slows down during its circular path, that's your tangential acceleration. Two horses on a merry-go-round. The horse on the inside is 7 meters from the center of rotation. The outside horse is 9 meters from the center of rotation. Which horse has the faster average speed? Well, I would tend to imagine at some point we have become witness to a merry-go-round and the horsies and hopping on the horsies.
Never been on one.
Or you may have been on one before, maybe when you were little. You don't remember when you were little and your parents took you out on one?
I never really, the only one I ever remember was at the fair and I was like scared of it.
Yeah. Alright. The music does it for you.
No, it's all the movies.
Like,
With like I'd always see like horror movies and like a merry-go-round would be
and the clown
trailer.
would come out and then you'd have a Scooby-Doo moment or
Yeah, and my parents would always hate like before movies when you go and there's like a horror movie trailer. My parents hated that because they're like, you're just scared of our kids.
When they have it like during like a kids movie.
Yeah, like the Avengers or something, and then you get a horror movie right before. Everyone on there going to
Yes, I can understand it. I don't know if I relate to it. I understand that. It's true.
So if the visor denominator was the radius, does that mean that whatever number is smaller is automatically going faster?
Okay, let's take a look at this. Okay, we could take a look at average tangential velocity is equal to distance divided by some time here, which is your circumference of the circle divided by time. Okay, distance divided by time. So we can always calculate velocity. How far have you traveled? How long did it take you to travel? One horse is 9 meters from the center, and a second horse is only 7 meters from the center. So if we take a look at the average tangential velocity, we we have 2 pi r divided by time. So if we look at the 9 meter and 7 meter horse, my tangential velocity, average tangential velocity is 2 pi times 9 divided by this time, or 2 pi times 7 divided by this time. Okay. And if we think about these two horses are one right beside the other.
Yes.
Okay? If they start at the exact same spot and they go around the circle and they get to that spot again, is one going faster? Is one going to get there faster? No. They're going to get there both at the exact same time. So if these both start side by side and they go all the way around the circle, the amount of time it takes for the inside horse or the outside horse to get around is going to be the same amount of time. So if we take a look at tangential velocity, we have 18 pi divided by this time interval, or 14 pi divided by this time interval. Which one has a larger tangential velocity? The 9 meter one. This one is larger. Because the time's going to be the same. So you might sit there and think to yourself, yeah, they're not actual horses. They are fixed horses that are moving up and down and up and down and up and down. But going around the circle, it's going to take the same amount of time to get around the circle. But the one that's on the outside has to go faster. Why? Because they're going the further distance. So that one has to go faster. A dog is sitting 1.5 meters from the center of a merry-go-round. The merry-go-round is set in motion. The velocity, the dog's tangential speed is 1.5 meters per second. What is the dog's centripetal acceleration? We can find our centripetal acceleration by taking the average tangential velocity squared divided by our radius. Well, we have a tangential speed, average tangential speed of 1.5 meters per second. Now we have to square. And the dog sits 1.5 meters from the center. Guess I've done this really nicely for us. Really don't need a calculator. Because I could cancel out one of my 1.5 meters.
Oopsies. It's not very observant. Look at that.
So it should come down to 1.5 meters per second squared.
Easy peasy.
Are you guys not here tomorrow? Huh?
I'm not.
Dallas has already told me he's not gonna be here.
Yeah, me too. Oh. What about Friday? Is on Friday?
I'll be here Friday.
Dallas?
Depends on if he's actually sick or not. Because if Dallas is sick now, then, but if he's just had a moment where he wasn't feeling great.
Maybe he just had a spell.
There was one time last year where I didn't eat for a day because I just forgot, and then the next morning I was like, my stomach was cramping. And
I
just
did
like,
That's
I did
not
the
fun.
opposite, like the week after I stopped taking my meds, which didn't make me hungry, I ate like an inhuman amount of food one day, and the next day I felt like it was the end.
I was like,
I remember that one. You're like, don't be.
Don't
feel
Can I
like
give everybody a second page of notes?
Little race cars on the bottom.
Yeah.
Sweet.
can you give it to me yesterday?
I thought I did too.
You know, Mr. Gregory, Mr. Grau was in here last week. He asked when we're taking our trip up to Cedar Point to look at stuff.
Found it.
Found it?
I put it in my cop stuff on it.
All right, inertia, an object is sent in motion, rests upon, thus act upon by an unbalanced force. Objects moving in a circular path are constantly changing direction, which means the velocity of the object, those change the velocity of the object. The object change of velocity occurs, the object experiences acceleration. Okay? They're connected together. They will continue to always connect together. When you talk about laws of physics, they will maintain throughout, no matter what your conditions are. Okay, the idea of inertia is let's go back. Let's set the dominoes back up again. Okay. The main guy who developed a lot of these physics stuff and put them down on paper for us humanoids to try to understand was Sir Philip Isaac Newton. Okay. Yes, there was all kinds of things that were developed prior to him, but they were all just passed around in regards to these are ideas that we have. Sir Philip Isaac Newton started formulating all these ideas and getting them down into a set world. And calculus was developed to explain all of these things from Sir Philip Isaac Newton. You have Newton's three laws of motion, the ideas of three laws of motion. The idea of inertia, that started everything. Okay, along from there he goes Newton's second law, which is force equals mass times acceleration. Okay, the proportionality idea. Newton's third law, for every force there's an equal but opposite force. I hit the wall hits me. Okay, so you have all these ideas here that have to maintain. These are fundamental ideas of physics. These are fundamental ideas that are utilized as all these other things are developed and explained. We can always revert back to these ideas. Objects moving in a circular path are constantly changing direction, which is a change of velocity of an object. If the change of velocity of an object occurs, acceleration must occur. Object experience acceleration. Well, Newton's second law, Sir Philip Isaac Newton's second law talks about the idea of an unbalanced force. Relates to the unbalanced force that is causing acceleration and a change in velocity. If acceleration occurs, a force must cause this acceleration. Once again, these are all intertwined and connected.
Second law of
Centripetal acceleration changes the direction of the object moving in a circular path. Once again, we have average velocity, tangential velocity divided by radius. The acceleration of this, which needs a direction, the direction is towards the center of the rotation once again. This is all just rehashing what we just talked about already.
So it's one half ice square feet. So what's this one using? Is it circumference? That's what the half mine is.
With acceleration, there must be a force keeping the object in a circular path. You need to have a force, because if you have acceleration, Newton's second law talks about acceleration and a force. Which leads us into what is called a centripetal force. That's a force applied to an object to keep the object moving in a circular path. Force is equal to mass times acceleration, so your centripetal force is equal to mass times your centripetal acceleration. So your centripetal force can be calculated by mass times Vt squared divided by your radius. Once again, these are things that you should probably also include in your formula sheet. And I don't know why on this green earth would anybody want to ever get on the swing, take it up 10, 20 stories, and then swing around on the swing. I don't know. I'm sorry. I'm not that type of person. I have an animate fear of falling. Okay? Which means I don't like heights. Because it's not the fear of heights that people have. It's the fear of falling from those heights. Okay, so I have a big fear of falling. And if I'm 10 stories up, swinging around on swings that I'm buckled in and there's ropes that are attached to mechanical devices are going to fail at some point. It may not be here, maybe not be now, it may be 10 years from now, maybe 20 years from now, but at some point it's going to be 20 years or 30 years. When will be that 20 or 30 years? I'm sorry, no. You will never, ever, ever, unless I'm 6 feet under, and if I'm a weekend at Bernie's, okay? If I'm weekend at Bernie's, they could probably plop me in there and strap me in, because I won't know the difference. Okay? But I need to be probably dead before they can strap me in there and say, oh, I'll enjoy this now.
You don't even see a little bit of fun in that?
No, none.
Not even a little
None. They're none.
What about like the giant like ball that you sit in and it like slingshots you up? And then
No.
down? I think that would be fun.
I have no enjoyment at all, see any fun and enjoyment at all at scaring the bejesus out of myself.
So is that why we don't do the Cedar Point?
Yes, exactly right.
I could agree with that.
I don't see any enjoyment in scaring the bejesus out of myself. I'm sorry. To go as a demon drop, even at the Wayne County Fair, you ride that up and all of a sudden, they let go and you fall down.
Yeah, don't do that one.
I'd rather do the ones that are stationary than like the ones that they move for fairs.
Yeah.
The worst one I was ever on, I did that at the state fair. Cause one of my friends was like, let's go do it. I'm like, sure, why not? I'll get my money's worth out of
And
my
the next day
gas."
somebody died.
And-
Somebody did that at the state fair, like, not the fuck.
Yeah, that was on the one that went around, and that was because they had a underlying condition.
Okay.
Going back to my point.
Yeah.
Everything has underlying conditions.
You still know it yet.
Yes.
And it's a really bad time to figure it out while you're spinning around on a loop and
Now,
you have a disease that when you spin around you pass out.
I will admit that I've done my dad duty. And when my kids want to go on roller coasters, I sucked it up, Buttercup. Okay? When we went to Disney World and I paid like $1 gazillion for my kids to enjoy Disney World, and I have to go along because I'm their parent. And you have, is it Magic Mountain the one that's in the dark? There's the one roller coaster that's, you go inside and it's all internal and it's all dark and you just see lights flashing all over the place. And that's it. You don't see how high you are. You don't see where you're going. Okay? I did that. I admit I did that one because I dad up. Okay? You have to dad up sometimes. But you know when you can buy that picture? You can buy that picture at the end because they snap a picture of you at a certain point, and you can buy the picture then for a memory keep. Okay, here's my picture. That was my picture.
Yeah, but that's why it's funny.
Yeah.
So your
Yeah.
grandkids will be like, oh, look at
My eyes were shut, and my head, my chin was buried right here because I did not, even though I couldn't see anything. I'm still there. But, so what's applying the centripetal force here is these chains right here that are mechanical metal that rust. Okay? They rust. Okay, NASCAR, we got some NASCAR people in here. Okay. We're going around curves. You're going around to Walmart down there. We talked about this the other day. We all NASCAR are going to Walmart down there. Okay, going up to the University of Akron. You got 2 lanes going from the Kenmore Leg. From 76 to the Kenmore Leg, then you have to go back around. But you got 2 lanes in there. Okay, hey, I'll admit, I NASCAR that. I'm passing on the inside straight. Okay, I'm passing on them. Semis on the outside going 30 miles an hour. I can go 35, 40 around that curve. Okay, I can pass them on the inside. They can pretty hot. I'm 1 step away from NASCAR. But what keeps the car going in a circular path? You have to have, you're going in a circular path, so you have to have centripetal force because you're changing velocity, you're changing or you have an acceleration. What keeps you going in a circular path?
I gotta say the wheels.
What about the wheels?
friction.
Bingo. Friction. You're partially right, but what about the tires? You have to have friction between the tires and the road. Because if you're going 40 miles an hour to Walmart down here, and it's icy, and it just has snowed, and you're going around the curve, and you're trying to go 40 miles an hour around that curve, you end up in the in that little pit, the gravel pit that they have way out there, and you just keep on going. So you have centripetal force, mass times centripetal acceleration, mass v/r squared. If the velocity is increased, the greater the force required to keep the car in a circular path. Because your centripetal force has to be greater. The greater the velocity, the greater the centripetal force. Now, there's a whole civics world that when you're in a civil engineer, they design roadways. They design that, okay? When you go along a circular path, or if you look at NASCAR, what do they do to help out the cars that go around the curves in NASCAR, or whenever you go on an off ramp? What do they do with the curves? Bank them, okay? They bank them. Okay? Friction between the road and the tires keeps the car from sliding off the road. Your force of friction is mu times force normal. Banking your curves increases your force normal. Because, okay, I'm going around a curve here and I'm on a flat surface, my force normal is the weight of the car. Remember what force normal was? It is the force equal but opposite to your force perpendicular. Okay? You have a flat surface, okay, your force perpendicular is just the way of the car. I take my surface from this and then I bank it. Now my force normal is going into the bank. Okay? So my force normal is going to be greater because my surface is not flat anymore, it is here. Because my force perpendicular, once again, force perpendicular to the surface. Here my force perpendicular is just my weight. Here my force perpendicular now starts turning into more of an angle. So when I increase my bank, I increase my force perpendicular. When I increase my force perpendicular, we increase our force of friction. When we increase our force of friction, that means our centripetal force gets increased. That is the physics problems. That is a design mode for off-ramps and NASCAR. Okay, when you go around the curves and if it's on a flat surface going around the curve, you have to go a little bit slower. But if you got a little bank there, I can ramp it up a little bit. I can flex the right calf a little bit more and push down. But if I am on just a flat surface, I don't have quite that force perpendicular anymore as I do with the bank. We will stop there today. We'll pick up there on Friday. Once again, civil engineers, this is what civil engineers do in regards to how they design roads. And even you have a speed limit that's suggested to go around the curves. Okay? There is a radius of that curve, and there's a center point in that radius of that curve. And as that radius changes bigger or smaller, velocity changes. So once again, there's a whole civil engineering